A tough math problem goes into two API calls. Same prompt, same question, but two very different models. A standard LLM call answers in a few seconds. It uses 723 tokens, and the answer is wrong. The reasoning model takes longer, a lot longer. The token counter keeps climbing 12,544 tokens for a single question, and it got it right. So the question is, what did this model spend all those tokens on? Here's a standard LLM call. Prompt goes in, single forward pass through the model, and tokens come out the other side. And here's the thing, the model uses the same compute pattern whether the question is trivial or brutal. What is 2 plus 2? It answers immediately. A hard combinatorics problem? It doesn't automatically stop and say, I should spend 10 times longer working this out. That compute pattern is mostly fixed at inference time. This is the box that reasoning models like O3 and R1 broke out of. The name for that shift is test time compute, spending more computation after the prompt arrives, while the model is answering. The question is, what does that extra computation actually do? The first clue came from a simple trick. Add 4 words to the prompt. Think step by step. Now the model doesn't jump straight to the answer. It produces intermediate steps. Step 1 becomes context for step 2. Step 2 becomes context for step 3. Each reasoning step is a new context for the next prediction. It's working memory the model didn't have before. But watch what happens when one step goes wrong. Step 3 takes a bad turn, and every step after inherits the mistake. There's no recovery mechanism, no second chance. Chain of thought is one line through a maze. It had the right instinct. Spend more tokens reasoning, but it's still a single path. No backtracking. If the model's first approach is flawed, there's nothing to catch it. But what if, instead of committing to one path, the model could branch? Here's what branching actually means. At a given step, the model has a distribution over many plausible next steps. In chain of thought, you sample once and follow that path. But you can sample multiple times and get different candidate next steps. Each one becomes a branch. How many branches? That's a parameter you control. Repeat that at each step, and one chain turns into a tree. Each branch pursues a different reasoning strategy. Some go deep, some hit dead ends. Now the model is no longer just reasoning, it is searching. And this is why the token counter explodes. Every branch the model explores costs tokens. Every step on every branch is another forward pass. Those 12,000 tokens. Think of them as the cost of searching that tree. But a tree creates a new problem. You have many branches, and without a way to tell good from bad, you're just spending tokens on noise. So now the problem has changed. The model no longer has one path. It has many. Some are useful, some are dead ends, and every one of them costs tokens. One obvious solution is to wait until the end and score the final answer. But by then, that whole branch has already spent tokens. Every step on the way there cost compute. And with many branches in play, that waste adds up fast. You need a way to catch bad reasoning earlier. Not just, did this answer end up right? But, is this step taking us in the right direction? That's what a process reward model does. At each reasoning step, it returns a score. High means this step looks promising. Low means the reasoning is going off track. And that score is used immediately. High score, keep growing. Low score, prune the branch before it wastes more compute. Now watch it on our problem. First step, set up the approach. High score. Second step, check small cases. High score again. Third step, generalize the pattern. Score drops. Not because the final answer is wrong yet, because the reasoning just went off track. That's the point. The score changes the search while it's happening. Better branches keep growing. Weak branches stop early. Explore, score, prune, continue. That's what turns a huge search tree into directed search. A quick aside. You might wonder where that score even comes from. Is the model just making up a number? No. That scoring function is learned, not improvised. During training, human experts work through thousands of problems and score each intermediate step. Not just whether the final answer is right, but whether each move along the way is sound. Often the signal comes from comparisons. Given the work so far, which next step is better? Over enough examples, the model learns to recognize good reasoning progress before the final answer appears. OpenAI's publicly released PRM 800K dataset contains 800,000 examples of step-level human judgments across 75,000 math solutions. That's the scale of supervision it takes to build a reliable step scorer. So when the scorer gives a step a low score, it's not a guess. It's a trained judgment, built from hundreds of thousands of examples of humans saying this move is right, this one goes wrong. Is all that extra compute actually worth it? Here is roughly how test time compute scales on hard benchmarks like ArcAGI as you give it more tokens to think. The pattern is surprisingly steady. Give it more tokens. Performance improves. Give it more again. Performance improves again. At the low end, the model follows a short reasoning path and answers quickly. At the high end, it explores more possibilities, checks more intermediate steps, and spends more time before committing to an answer. That is why reasoning models can use thousands, sometimes tens of thousands of tokens on a single problem. And that gives you a control knob. Set the thinking budget low, fast, cheap, less exploration. Set it high and now it's slower, more expensive. But you get more chances to catch mistakes before answering. For a decade, the main way to make models smarter was to train bigger models. This curve suggests something different. The same model can sometimes get better results simply by thinking longer. But there's an honest constraint. More search only helps when there is something to search toward. For open-ended tasks, write a poem, brainstorm ideas, draft a strategy, there may not be one clean target. The model can generate more options, but it cannot always know which path is truly better. What test time compute needs is a signal, a way to tell whether a step is moving closer to the answer or farther away from it. Math has that. Code has that. Logic puzzles have that. Some planning problems have it too. And when that signal exists, those extra tokens are not waste. They are the model buying more chances, exploring branches, cutting off bad paths, recovering before the final answer. A standard model gives you one path through the maze. A reasoning model pays to search the maze. More tokens, but better reasoning.